Welcome to week 8. We are finishing up our year talking about energy, and today is the first lesson for the week, part A. Your objectives today is just going to be how to determine potential energy and kinetic energy of a system. But potential energy, if you remember, you can calculate with mgh, mass times little g, 9.8 times the height. It's the energy stored in the Earth's gravitational field. So at any time you lift something, anytime something goes up in the air a certain height, the potential energy is the mass of that object times 9.8 gravity on Earth in joules. Kinetic energy, on the other hand, is the energy of a moving object. It's 1/2 the mass of the object times velocity squared. Velocity squared, the square is the important part because it means when you double your velocity, you get 2 times 2, 4 times the energy. When you triple your velocity, you get 3 times 3, 9 times the kinetic energy. So these are our two energies that we're going to focus on today. Potential energy and kinetic energy. Here's an example we had last time of lifting a boulder above a bunny. Okay, so let's say we have this boulder and we lift it up 5 meters. It's a 200 kilogram boulder lifted up 5 meters. You did work. Work equals force times distance. This is another way of putting it for potential energy. And just to review, go ahead and calculate. We're going to calculate how much potential energy you gave this boulder by lifting it. So looking at our equation, looking here, look at our situation, what goes in this first box for figuring out the work or the potential energy for lifting the boulder? Okay, it is the mass. The mass goes there, which is 200 kilograms. That's the mass of the boulder. What goes right here in this second spot? It is little g, 9.8 meters per second squared on Earth. And then finally, this third spot, what goes in this third spot? H is the height. We lifted it 5 meters. So 200 kilograms times 9.8 meters per second squared times 5 meters. And you put in your calculator, and you end up with 9,800 joules of energy. That's how much work you did to lift this boulder, and that's how much energy is stored in. Potential energy is the boulder sitting here above the bunny, 9,800 joules. All right, so why do we care about that? Well, we're going to start using that today. First, let's compare to back when the boulder was on the ground. How much potential energy does the boulder have once it reaches the ground? If I drop it and let it land on the ground, sitting here, down here on the ground, what's the gravitational potential energy of a boulder just sitting on the ground? I'll give you a hint. You're going to have to figure out the height. So what is the height of the boulder? It's 0. It's on the ground. So the height's 0. So since the height is 0, how much potential energy does this boulder have sitting here on the ground? 0 height means 0 potential energy. No potential energy. It's just sitting on the ground. Once it's sitting on the ground, it's just sitting there. No potential. So this begs the question, if you give a boulder 9,800 joules of potential energy by lifting it, and then you drop it, what's going to happen to the energy in the boulder, right? As the boulder moves down, it's going to lose height. So it's going to lose potential energy. But something amazing happens. It turns the potential energy into a different form of energy. It'll turn it into kinetic energy because it's going to speed up. As a boulder falls, it loses potential, but it gains speed. It loses height, gains speed. So it will gain kinetic energy on the way down. And we know once it hits the ground, it has no more potential, but it has lots of speed. So the question is, how much kinetic energy will this boulder have? Once I let go of it and it falls 5 meters back down, how much kinetic energy will it have right before it hits the ground from its motion? So before we answer that question, let's take a detour and look at another example, and then we'll come back and see if we can figure out the answer to this question right here. What I have here is a simulator, online simulator that simulates the motion of a pendulum. And I have this red pendulum hanging down here. You can see the information. The length is 0.7 meters, but we don't really care about that. The mass of this pendulum is 0.5 kilograms. We're going to be using that later. The mass of the pendulum, 0.5 kilograms. I'm going to click on pause so it doesn't start moving right away. I'm going to lift this pendulum up to about right here. And notice on this side here, this is a graph of the energy. I want to zoom in a little bit. This is the graph of the potential energy of this pendulum. Okay, if I bring it down here to the bottom, the potential energy is 0. If I bring it up a little bit, the potential energy goes up. Bring it up more, it goes up. And I bring it up to here, it goes up here. This is the potential energy. So I also want you to notice that this is the energy total. This is all the energy in the pendulum, and it's not moving. So there's no kinetic energy. All the energy is potential energy. So let's calculate, before I let this thing swing, let's calculate how much potential energy did I give this mass by lifting it. To do that, I'm going to take out a ruler. I'll move it over here. And I had this blue one here so I can keep it. I'm going to put this right on the 50 mark. Move it over like this, and we can get our height. So here I have the snapshot. You can see the information for the pendulum. Right, we have the red pendulum, we have its mass right here, okay, and then the height is from 50 mark, and it went up to here like this, and we can see this is in centimeters, so 10, 20, 30, 5 centimeters, which is 0.35 meters, okay, and the question is, how much potential energy does this pendulum have? So our givens, M, what is the mass? What goes right here? 0.5 kilograms is the mass. And then G, what is little g? On Earth, little g is 9.8. And then finally the height. What was the height? 0.35 meters is how far I lifted it up. 0.35 meters. Guess. So GU, so the unknown, we're solving for potential energy. And then GU equation, the equation, potential energy equals mgh. And then S, substitute. So I'm going to take this equation and substitute in. So potential energy equals, all right, so what's my first number? It's M. M is 0.5. And then what's my second number? It's G, and G is 9.8. 9.8. And what's my last number? It's H, and H is 0.35. Okay? So potential energy is 0.5 times 9.8 times 0.35. And so the final is solve. S, guess, G-U-E-S, solve. Potential energy equals. So now I'm going to put this in my calculator. 0.5 times 9.8 times 0.35 is 1.72 joules of energy. All right, that's how much potential energy that this pendulum has right here when I lifted it up. So let's get rid of our ruler now. Okay, so now that's how much potential energy it has, and what we want to do is hit play and let it do its thing, and look what happens. So as it swings back and forth, over here on the left, we have the graphs of our energy. Now, potential energy, this is going too fast. I'm going to go slow motion so we can get a little better idea. So let's watch potential energy. Let's pay attention to potential energy for now. All right. So as the pendulum goes up, the height goes up. So mgh goes up, and then as the pendulum goes down, the height goes down. So energy goes down. As it goes back up again, it goes back up. Let's pause it right there near the bottom. Look at the potential energy. Zero potential is at the bottom, no height. And I'm going to pause again at the top. Right there. Right there is the maximum potential because it's the maximum height. And so potential energy just keeps going back and forth. It goes up and down and back up again. And just keeps doing that as it swings. That's the mgh. Now let's look at the kinetic energy. Kinetic energy looks like it's, well, watch these two, potential versus kinetic. What do you notice about the kinetic energy versus the potential energy? How does the kinetic energy compare to potential energy? You could say they're opposites because as potential energy goes up, kinetic energy goes down. Potential energy goes down, kinetic energy goes up. What's happening here? Well, let's look at this third column. It's called energy total. This is the combined energy when you add up both energies of the pendulum. So let me stop at the top for now, right there. Okay, the whole energy of the pendulum is all potential because it's not moving. It goes all the way to the top and stops, and then it's not moving. It's all potential. So we have our energy total, and we already calculated the energy total. It was 1.72 joules of energy. That's the total energy. And then as the pendulum swings back down towards the bottom, it's speeding up. It's picking up speed, it's picking up kinetic energy and losing height, potential energy. So it's all kinetic energy here at the bottom. And look, the kinetic energy at the bottom, all the energy is kinetic energy. So the kinetic energy at the bottom is, guess what? The 1.72 joules energy that we put in it in the beginning. And then as the pendulum goes back to the top again, it's all potential, all height, and it slows down and stops again. No kinetic. So what we notice is the total energy, if you look at the bar here, what's happening to the total energy the whole time? Is this total energy right here, look at the top of the total energy, is total energy staying the same constant, or is total energy going up, or is total energy going down? Is total energy of the system increasing, decreasing, or staying constant? Well, it's staying constant. The total energy is staying constant. Energy is conserved. So that's our main idea. This is our last main idea for the year. Conservation of energy. Conservation of energy. The total energy of a system is conserved. This means that if we track the joules of energy flowing in and out of the system, we know how much energy remains in the system. Potential plus kinetic is constant. Potential plus kinetic adds together, stays constant. And it equals for this pendulum, it equals the total amount of energy that we put into the pendulum when we lift it. We did work, put in 1.72 joules of energy, and then once we let go of the pendulum, it stays at the same amount of energy the whole time. And so what happens is, as potential energy decreases, the kinetic energy has to take up the remaining space. And that's why kinetic and potential energy seem to be opposite in this graph. So how can we apply this to our example with the boulder and lifting the boulder and dropping the boulder? Well, we did 9,800 joules of energy work to lift the boulder, and that's the potential energy stored. And when we drop the boulder, it's converted into kinetic energy. My question is, how much kinetic energy does this boulder have when it hits the ground? I'll give you a hint. The potential energy equals 0 when it gets to the ground. So how much kinetic energy does it have when it hits the ground? Energy is conserved. So if we did 9,800 joules of energy to lift it, that means it still has 9,800 joules when it hits the ground. And that's all turned into kinetic energy. So 9,800 joules of kinetic energy. That's how much energy it has when it gets to the ground. And actually, once it gets to the ground, now the energy is converted into other things. Hits the ground, and if it lands on the bunny, that's not good. It's turned into all these other forms of energy. It doesn't just disappear. The energy turns into heat. The rock boulder heats up a little bit when it hits the ground. The ground heats up a little bit when it hits the ground. The bunny heats up when it hits the bunny, and also, it does work to the bunny and crushes the bunny in force and distance, but also makes sound waves, and that's energy. And then, by the way, there's also, as the boulder was falling, it was falling through the air, and it was warming up there, moving the air and warming the air up. So heat in the air and giving the air kinetic energy, moving the air around. So all these forms of energy, they all add up. All these forms of energy right here at the end add up to the energy, the kinetic energy of the boulder dropping, which adds up to the energy that you gave it when you did 9,800 joules of energy. Conservation of energy. Energy is conserved. It's one of the main ideas in science. Let's go back to our pendulum real quick and to see how this works out. I'm going to let this swing on normal, okay? So here's our pendulum swinging like normal, but this is not exactly realistic, okay? Because we have friction set to none. And in real life, there's air in the way. And this pendulum has to swing through the air and has to push the air, which is friction. And also, there's a little bit of friction up here at the top where the string is, where the wire is attached to the top. So what happens with that is when we add friction, I want you to notice something. I'm going to add a little bit of friction like this. This is more realistic when we have friction. I want you to notice, look over here. Thermal energy, right? Energy is being converted. The friction, as this moves through the air, it warms the air up. As it moves through this little point here, it warms the string up. The mass is warming up, and it's turning into thermal energy. And look what's happening to our energy now. The total energy stays the same, but as the thermal energy increases, there's less energy left over for the pendulum itself. And look what's happening to these. These two, the kinetic and potential, have to fit. I'm going to slow this down. Okay? As things are heating up, it's almost like energy is being lost. It's not being lost, it's just being turned into heat, and heat's not as useful energy you can't get the energy back out when it's heated up. So it looks like the energy is lost, but this thermal energy goes into the total energy, and now we only have a little bit of energy left over for the potential and kinetic. So this gets smaller and smaller as time goes on. More heat means less and less energy left over for kinetic and potential. And look what happens to the pendulum. If you notice, what happened to the height of the pendulum? It's not going as high anymore, right? And this is what happens in real life, because energy, we say energy is lost. It's not really lost, it just changes into heat. Joules of heat. Okay, I'm going to let it play again in regular speed. And as things heat up, again, look what's happening to potential and kinetic. Okay, eventually, there's so much heat created that the pendulum gets slower and slower and lower and lower and slower and slower and lower. Okay, until it's all converted back into thermal energy. So in the end, this process models almost everything you see happening around you in the world and anything you do. Almost every time when you have energy, you start doing some kind of work and it turns into motion, but there's friction and it changes into heat, and ultimately what happens is all the energy changes into heat and goes into the environment as heat, and is not in a very useful form. But the point still remains true, that energy is conserved. It stays, the total energies and joules is still there. It didn't just disappear, it turned into heat in this case.